In this lesson, I can find conjugate pairs of complex zeros of polynomial functions, and I can use the fundamental theorem of algebra. What are complex conjugates? They are pairs of complex numbers of the form a plus bi and a minus bi. Okay, so they look the exact same, it's just that plus or minus sign varies in between. It's important to note that if f is a polynomial function with real coefficients, and you're given that a plus bi is an imaginary zero, then a minus bi has to also be a zero. This is really similar to what we did in the last note example, right? Like we talked about irrational conjugates, right? If 1 plus root 3 was a zero, then 1 minus root 3 had to be a zero. Now we're just doing the same thing with imaginary numbers. So if 3 plus 2i is a root or a zero, then 3 minus 2i has to be a root or a zero. It says down here, remember to use this rule, x squared opposite sum x plus product, as a shortcut anytime you see a conjugate. Okay. So in this example, it says using zeros to write a polynomial function. Write a polynomial function of least degree that has rational coefficients, a leading coefficient of 1, and the zeros 2 and 3 plus I. So I have a 0 of 2. I have a 0 of 3 plus I. And if 3 plus I is a root, what else has to be a root? 3 minus I has to be a root by this theorem up here, the complex conjugates theorem. Okay, now as soon as I see conjugates, right, these are conjugates, I'm going to use my rule, x squared opposite sum x plus product, to help me quickly write a factor for those two solutions. So what would be the sum of these two solutions? If I add 3 plus I and 3 minus I together, what do I get? The i's cancel and I'd end up with 6. So I'll have x squared opposite of my sum times x plus, and now I need to know what the product is. What is the product of 3 plus I times 3 minus I? Well, if I multiply this out, we get 9 minus 3i plus 3i minus I squared, right? Because they're conjugates, the middle terms cancel. And what is I squared? Don't forget to replace I squared with -1, right? So really this is like 9 plus 1, which is 10. So if I add on the product, I'd have plus 10 for that factor. Okay, what's the factor for 2? That's going to be x minus 2. And from there, we just have to multiply it all out, right? First times first gives me x cubed. Multiply through to the second term, we get minus 6x squared. Multiply through to the third term, we get plus 10x. Okay, moving inside, we get minus 2 times x squared is minus 2x squared. Minus 2 times minus 6x would be plus 12x. And minus 2 times 10 would be minus 20. Add it all up. We get that our function is x cubed minus 8x squared plus 22x minus 20. There we go. All right, so down here just has you doing some of these examples yourself. Go ahead and pause the video and take a look at A and B and see if you can figure these out. Welcome back. For A, let's just talk about what my solutions are. They'd be -1, 4i, and really if 0 plus 4i is a solution, then what else has to be a solution? 0 minus 4i or -4i. Again, I see conjugates here, right? So I'm going to use x squared opposite of the sum. What's the sum? Sum. If I add these together, they just cancel each other out, right? So my sum is 0. Plus, what's my product? If I multiply these together, what would I end up with? That'd be -16i squared. Remember, what's I squared? -1, so positive 16. So my factor is x squared plus 16 And then this would become a factor of x plus 1. Okay, and then with some work multiplying that out, you could get to your final answer. I'll let you do that. Over here, if I'm given root 2 as a root, right, 0 plus root 2, then what else has to be a solution? Negative root 2, right? The conjugate, 0 minus root 2, would also have to be a solution. All right, I'm also given that 1 minus 3i is a solution. So what else has to be a solution? 1 plus 3i. Again, I'm going to use my rule, x squared opposite sum x plus product, to write the factors for those conjugates. So here the sum would be 0, and the product would be what? So it'd be negative root 4 or negative 2. Okay, so my factor here would be x squared opposite sum x plus product, or x squared minus 2. And what would I get if I did the same rule with these conjugates? What would the sum be if I add these together? Well, the imaginary parts would cancel and I'd be left with 2. What's the product of these conjugates? You have 1. This would be plus 3i. My insides would give me minus 3i. And last would be minus 9i squared. Right? I'm not surprised that the middle part's canceled, because it was a difference of 2 squares that we end up with here. And what's I squared going to be? What do we replace that with? Negative 1. So really this becomes 1 plus 9, or 10. So writing it using my rule, I have x squared opposite sum x plus product. So that's what I would put as my factor for those two conjugates. Okay, so writing that down here, I would get x squared minus 2 times x squared minus 2x plus 10, right? If we put both of these parts together, and then you can keep multiplying that out to get your standard form of your function. Okay, but that's the process I would go through. For the next core concept, this is where we get into the fundamental theorem of algebra. This is super important. It says, if a polynomial has a degree n, then the equation has exactly n solutions. So the degree equals the number of solutions. That's the big shebang here. Okay. It also says that each solution repeated twice is being counted as 2 separate solutions. Each solution that's repeated 3 times is counted as 3 separate solutions, and so on. So we need to pay close attention to those solutions with higher multiplicities, because we'll be counting each of those as separate solutions. The theorem says if a function is a polynomial of degree n, then the equation has at least one solution in the set of complex numbers. So let's just talk a little bit about complex numbers. Complex numbers is your broad umbrella term, right? We write them in the form a plus bi, and those complex numbers include both your real part and your imaginary part. Okay, so real and imaginary numbers both fall under that broad category of complex numbers. So by saying that if we have a degree n polynomial, then there's got to be one solution in the set of complex numbers, that's a very broad statement. Okay, of course, we're going to get a real solution or an imaginary solution. And even under the real heading, real numbers could include rational numbers, which are fractions like 1/2, 2, 2/3, or real numbers could also mean irrational numbers, like maybe like 1 plus root 3. We could just have like root 2. Okay, rational numbers, we typically see those roots. Irrational numbers are also things like pi. Okay, imaginary numbers just have I in the expression. Okay, so down here it says, long story short, an nth degree polynomial function has exactly n zeros where the repeated zeros are going to be counted more than once. That is like the big star this main point of the fundamental theorem of algebra that we're going to focus on today. It says the following table shows several polynomials and their solutions, including the repeated solutions. Notice that for the last equation, the repeated solution, -1, is counted twice. So we're counting that as two separate solutions. So let's look closer at this chart. Okay, notice the highest exponent here in the first equation is 1. So it's a degree 1 polynomial. We have one solution, and it's 1/2. Here, the highest exponent is 2. So it's a degree 2 polynomial. And so we should have two solutions, right? We'd have both the solutions √2 and -√2. Okay. Here, the highest exponent is 3. So we say that it's a degree 3 polynomial. The degree is equal to the number of solutions. So 2 is a solution. And then this can really be broken into two separate ones. We could have -1 plus I radical 3 and -1 minus I radical 3. Okay, so there's our 1, 2, 3 solutions. Okay, notice the solutions could be real, they could be imaginary, they could be rational, they can be irrational. Here our highest power is 3. So we say it's a degree 3 polynomial, so there must be 3 solutions. Really, we only have 2 distinct solutions. It's just that -1 has a multiplicity equal to 2. So we're going to see actually a bounce happen on our graph at -1, and then our graph's going to cross at +1. Okay, but we count those repeated solutions with higher multiplicities as 2 separate solutions. So if I was counting these, I'd say 1, 2, 3. Notice I count -1 twice. We count those repeated solutions as separate solutions. Okay, so in example 2, it says finding the number of solutions. How many solutions does this equation have? Okay, and we're assuming when we're saying number of solutions, we're assuming that repeated solutions would be counted more than once. So here this is a degree 3 polynomial, so it should have 3 solutions. Again, I'm just going to put repeated solutions counted more than once. Okay, so whenever we're talking about number of solutions, we want to keep in mind the repeated solutions are going to be counted more than once. Okay, so let's go ahead and graph this function on our calculator and see what it looks like. So in my calculator, I'm going to go to y equals, clear out what I have, and let's type in that function. We have x cubed plus 3x squared plus 16x plus 48. Looks like this. If I graph it, we see a 0 at -3. And that's really it. So that's kind of weird. Let me go back. It says, look at this function on your graphing calculator. Why don't we see 3 solutions? Well, what could be happening? Right now, I only see 1 solution, but I know there should be 3 solutions. What could be happening? Well, some solutions may be imaginary, right? If we have an imaginary solution, we're not going to see that show up on our graph as an x-intercept. We also might have this solution at -3, right? Solution at x equals -3 may have a multiplicity more than 1, right? Maybe we're counting -3 as 3 separate solutions. I don't know. The multiplicity might be greater. It's hard to know. Okay, so let's figure out what's actually happening. We saw that we had a 0 or a root or a solution at -3. So let's actually use synthetic division here. If I put -3 outside and then I list my coefficients up top, this would be 1x cubed 3x squared, 16x, and 48. Let's go ahead and just quickly do this synthetic division. 1 times -3, add down. 0 times -3, add down. 16 times -3. 16 times -3 would be -48, and add down. So we do get a remainder of 0, which is good because that means that -3 is a solution or a root. Okay, my factor was x plus 3 for that, and this divisor would be x squared plus 16, right? If this is my function, and I want to get my solutions, I'd set each factor equal to 0 and solve. So I would subtract 3 on both sides here. We get one solution is -3. And here, if I subtract 16 on both sides and then square root both sides, what am I getting as my answer? Well, the square root of 16 is 4, but what do I need to put if I have a negative under a square root? This would be plus or minus 4i. Look at what I have. I've got 3 solutions, but 2 are imaginary. So that's really interesting. I have 3 solutions, but 2 are imaginary. I have x equals -3 as a solution. I have x equals 4i as a solution. And I have x equals -4i as a solution, which is why we were only seeing one of those zeros show up on our graph. So we did confirm that we got 3 solutions for our degree 3 polynomial. How many zeros would this function have? What's the degree of this function? The degree or highest power is 4, so it should have 4 solutions. Remember, we are counting repeated solutions more than once. It says look at the function on your graphing calculator. So again, I'm going to go back to my y equals. I'm going to type this in. We have x to the 4th plus 6x cubed plus 12x squared plus 8x. Okay, just type that in my calculator and press graph. So I see a root at -2, and it looks like I have another x-intercept at 0, right? So at -2, I see an x-intercept, and at 0, I'm just going to make a note of that. I see a 0 at x equals -2, and I see one at x equals 0. So the question is, why don't we see 4 solutions? I only see -2 and 0 on my graphing calculator. Well, again, we might have some imaginary, right? Could have imaginary roots or zeros. Why else could we maybe not be seeing all 4 solutions? Maybe x equals -2, or when x is 0, those x-intercepts have a multiplicity more than 1. Have multiplicities more than 1. Because remember, we would count those as separate solutions. So a couple different things could be happening. Let's go ahead and see what's actually happening. All right, so I'm going to go ahead and test -2 and just see what's going on there. After do synthetic division, we have 1x to the 4th, 6x cubed, positive 12x squared, 8x, and then don't forget, we don't have a constant, so I do need to put a 0 placeholder in for where the constant would go. Okay, so 1 times -2, add down, 4 times -2, add down, 9, 10, 11, 12, that'd be 4. 4 times -2 is going to be -8, add down, and then we end up getting 0 times -2 is 0, and then if we add down, we would get 0. Okay, so this is my remainder. My constant 0, this would be x, x squared, and x cubed. So if I was writing my polynomial function, my divisor is x plus 2, and my quotient would be x cubed plus 4x squared plus 4x. There is a GCF in that quotient. They're all divisible by x. So I could factor out the x, and if I do that, I would get x squared plus 4x plus 4. And I'm going to move the x out front. I like it if it leads. So I'll have x times x plus 2 times, and if I factor this, that would be what, x plus 2 times x plus 2. So really, if I set each one equal to 0 and solve, I'd have a solution at 0, -2, -2, and -2. Look at that. Look at my solutions. X equals -2, -2, -2, and 0. So you can see I have 4 solutions. It's just that -2 has a multiplicity that's more than 1, right? -2 has a multiplicity of 3. And actually, it's interesting because let's just observe what's going on at -2 on our graph. Okay, so going back to my graphing calculator, take a look at what's happening at -2. Do you see how there's like a curvature? Like how at -2 it comes down and my graph kind of curves as it crosses? If there's any kind of curvature, that is an indication that it's going to have a higher multiplicity. So it crosses through, but there's curve. At 0, see how there's no curve? That's when I'm like, okay, it's crossing, so it's odd multiplicity, but I'm going to say that it's just a multiplicity of 1. Okay, so a cross means odd multiplicity, but because of that curve, I would think that it's going to still be an odd multiplicity, but a number bigger than 1. So like maybe an odd multiplicity of 3, 5, 7, okay, a higher multiplicity. Okay, so I'm just going to make that note. Looking at x equals -2 and x equals 0 for that problem, we knew that both of them were going to be an odd multiplicity because it crossed, right? Odd multiplicity because of the cross. But with -2, there was a slight curvature, right? I'm guessing that the multiplicity here was a number bigger than 1 because of the curvature. Okay, whereas at 0, this was going to be an odd multiplicity, but I'm guessing that the multiplicity would be equal to 1, which that 1 looks kind of crazy, because there was no curvature. There was no curve as it crossed over. So just some things to keep in mind. How many solutions would this equation have? Well, the highest power is 4, so I would say 4. How about this one? Well, the highest power is 3, so I'd say 3. Okay, you just look at the highest power, keeping in mind that some of the solutions might be repeated or some of the solutions might be imaginary. All right, so here it says find all the zeros of this function. Let's start with the degree. The degree is 5, so the number of solutions should be 5. Step 1, we're going to graph this function on the calculator to find a rational root that makes sense to test, right? We're looking for the x-intercepts. As we look at the x-intercepts, we're going to look to see if there might be possible repeated solutions by analyzing the behavior. So remember, if there's a curvature through a cross, then it might have a higher multiplicity, or if there's a bounce, then that means that there's going to have to be an even multiplicity. Okay, so going back to my calculator, I'm going to zoom out a little bit here. Going back to y equals, let's type this in. We have x to the 5th plus x cubed minus 2x squared minus 12x minus 8. Graph. Okay, so I went ahead and put in my y equals, and then I press graph. Right. See if I look at my y equals here. That's where I typed it in, and then I press graph in the top right-hand corner here. Now look at what I have. It looks like -1 and 2. I have x-intercepts. At -1, there's a bounce, so I know that that's going to be an even multiplicity. And at +2, there's a cross, so I would say that has to be an odd multiplicity. And look at where it crosses. Is there any kind of curvature where it crosses? No. So I would say that that odd multiplicity is probably just equal to 1 rather than it having an odd multiplicity of 3, 5, 7, etc. Okay, so the even multiplicity is obviously going to be a number bigger than 1, right? An even multiplicity could be a multiplicity of 2, 4, 6, etc. But this one has an odd multiplicity of just 1, is my prediction. Okay, so I'm going to write that in, that I have a root at -1. And that bounced at the graph there, so I'm going to have an even multiplicity. And then we also had a root at 2, and that was a cross, and it was a cross with no curvature. So I'm guessing that it's just going to be a multiplicity equal to 1 rather than a multiplicity of 3, 5, etc. So now we're going to use synthetic division, factoring, maybe quadratic formula, maybe square roots to solve. And we're going to write our solutions and multiplicity of each solution. So let's just pick one of those to test first. Do you want to test -1 first, or do you want to test 2 first? Let's go ahead and let's start with -1. Okay, I'm going to start with -1. I'm going to list out my leading coefficients. We have 1x to the 5th. We don't have anything for x to the 4th in here, so I'm going to have to put a 0 placeholder. 1x cubed, -2x squared, -12x, and -8. Bring the first down. Multiply 1 times -1, add down. Multiply -1 times -1, add down. Multiply 2 times -1, add down. Multiply -4 times -1, add down. Let's see, 12, 11, 10, 9, 8. That'd be -8. Then -8 times -1 is a +8. And we add down to get a remainder of 0, which is what we like to see if that's truly an x-intercept. So now normally I would write my function in the form divisor times quotient. In this case, my divisor, or what I was dividing by, was the factor x plus 1. And my quotient, if we have that this is the constant, that's x squared, x cubed, and x to the 4th. We'd have 1x to the 4th. That would be minus 1x cubed plus 2x squared minus 4x, and then minus 8, which, that's a lot of terms. That is 1, 2, 3, 4, 5 terms. Do we have a factoring technique for 5 terms? No, right? We don't have a factoring technique for 5 terms. Can't factor 5 terms. So what am I going to do? I'm going to do synthetic division over again. I'm going to go back over here, and I'm going to keep synthetically dividing until I can easily factor it, or until I get down to a quadratic function where if I can't factor it, I can use the quadratic formula. Okay, so what do I want to use? Should I use, do I want to use -1 again? I could, because there was a bounce there, so I know it's going to be a repeated solution, or we could try to use 2. Let's go ahead and let's just make a decision to use 2. I'm just going to do something different. So when I do synthetic division again, we put the 2 on the outside. Remember the remainder, we're not going to use that in this synthetic division process. Bring the first down. We have 1 times 2, add down. 1 times 2, add down. 4 times 2 is 8, add down. 4 times 2 is 8, add down. So this is my remainder. So again, we got that 2 as an x-intercept. That looks good. And now I have 2 divisors, right? Not only was I dividing by the factor x plus 1, but now I'm also dividing by x minus 2 as a divisor. So let's see what I can do over here now. If I'm writing my function as divisor times quotient, my divisors were x plus 1 and x minus 2. And what was my quotient? Well, this is the constant x term, x squared term, and x cubed term. So I have x cubed plus 1x squared plus 4x plus 4. That is 4 terms, so I could try to factor that by grouping. So if I was going to factor something out of my first group, I'd factor x squared out, and I'd be left with x plus 1. And in the second group, I'd factor a 4 out, and I'd be left with x plus 1. Woo, yay, that works. That's looking like that's working for us, right? I could finish factoring this by grouping. They both have an x plus 1 in common. And then the x squared plus 4 would be left over when you factor out x plus 1. Okay, and that's it. That's completely factored. The x squared plus 4, I could factor down more if it was x squared minus 4, right? We could use a difference of 2 squares, but it's not. It's plus. So that's about all I can do there. If you wanted to do synthetic division one more time, you could. You're going to get the same result. I could go back and use -1 again since it bounced there and it was a repeated 0. If you wanted to, you could have done it again with -1, right? 1 times -1, add down. 0 times -1, add down. 4 times -1, add down. And you can see I get my factor x squared plus 4, which is what I had over here. Okay, so you have a little bit of flexibility on what you want to do. I'm someone where as soon as I can see that I can use factoring, I just stop using the synthetic division. Okay, so here's my factored polynomial. We've got x plus 1, x minus 2, x plus 1, x squared plus 4. Alrighty, and if I want to set each factor equal to 0 and solve, let's see what we'd get. We would end up with x equals -1, x equals 2, x equals -1, and then here we'd get x squared equals -4, which when I square root both sides, we'd get plus or minus what? Well, the square root of 4 is 2, and then because it's a negative under the root, we'd get 2i. So I've got x equals -1, and what's the multiplicity? That is being counted twice, right? It's a multiplicity of 2. We could have written that factor as x plus 1 squared if we wanted to, but I'll leave them separated. We have x equals 2, and it looks like that just happens once. It has a multiplicity of 1. And then we have x equals 2i and x equals -2i, which those solutions aren't going to show up on our graph anyway. But let's count how many solutions I have. Remember, I was supposed to have, what, 5 solutions because it was a degree 5 polynomial. So let's count how many solutions I had. We ended up with 1, 2, 3, 2i was 4, and -2i was 5. Notice that we had to count some imaginary solutions that we didn't originally see on our graphing calculator. And because there was a bounce at -1, we had to count that as 2 separate solutions, right? So higher multiplicities get counted multiple times, right? If I add all these multiplicities together, it should add up to our total number of solutions, right? Now, -1, we're counting twice. So that's 1, 2, and we have 3, 4, 5 total solutions. All right, so in this student practice, try to pause the video and see if you can do this one. Welcome back. Let's go ahead and plug this into our calculator. I'm just going back to my y equals and typing in x cubed plus 7x squared plus 16x plus 12. Here we are. I'm going to press graph. Okay, there's a couple things happening. It's hard to tell where it crosses. I'm going to zoom in. I'm going to zoom in, and I'm going to just move my little crosshair over here because I want to see this section of the graph closer. Looks like I cross at 1, 2, 3. It looks like I have a cross at -3, and it looks like I have a bounce at -2. So cross at -3 and a bounce at -2. I'm going to make a note of that. Cross at x equals -3 and bounce at x equals -2. So I'm expecting this multiplicity probably just to be 1 because it didn't look like there was curvature at that cross. And at the bounds, obviously, it's going to have to be a multiplicity more than 1 since that's going to have to be an even multiplicity. So maybe a multiplicity of 2, 4, I don't know. Like it's going to have to be some kind of even multiplicity. So keeping that in mind, let's just pick one to do synthetic division with. This is a degree 3 polynomial, so I am expecting 3 solutions. So it would make sense to have a multiplicity of 1 and a multiplicity of 2, because that would add up to 3. So I don't think we're going to have any imaginary solutions here, but let's see. Okay, I'm going to put the negative 3 outside. I have 1x cubed, 7x squared, 16x, and 12. 1 times negative 3 is negative 3. So that'd be 4. 4 times negative 3 is negative 12. That's going to be 4. And then 4 times negative 3 is negative 12. We get the remainder of 0 that we were expecting. I'm going to write my function as divisor times quotient. What was I dividing by? Well, if the factor, or if the solution was negative 3, then the factor would be x plus 3. And what was my quotient? This is remainder, constant, x squared. So I get x squared plus 4x plus 4. And that I can pretty easily continue factoring. We're going to have x plus 3. And if I factor down that trinomial, x times x is x squared. 2 times 2 is 4. And I'm going to put plus signs. And so there we go. If I set each factor equal to 0 and solve, I would end up with x equals negative 3, x equals negative 2, and x equals negative 2. So there you go. There's my 3 solutions. Right? It was a degree 3 polynomial, should have had 3 solutions. Here's 1, 2, 3. Where negative 2, we're having to count it twice. And that was expected because there was a bounce at negative 2. So I'm not surprised there. So I can write my factored form of my polynomial here. We have x plus 3 times, let's go ahead and write this as x plus 2 squared. You could leave it as x plus 2 times x plus 2, but I'll write it as that binomial squared. The solutions were negative 3, and it had a multiplicity of 1, and negative 2, and it had a multiplicity of 2. Excellent. All right, if you're interested in another triple synthetic division problem with a quadratic formula this time, take a look at the enrichment video.